So, so now I want to explain MAML, which is model agnostic meta learning, and we are here. So in lecture 1, I explained matching networks. In lecture 2, I explained protonet. In lecture 3, I explained relationnet. And now we are focusing on meta-agnostic meta-learning, model-agnostic meta-learning. And this is the Bayesian version of that, very important article. These are Bayesian approaches to MAML that I will explain today. And this is good if you want to do it faster. Because, MAML has lots of iterations. You need to have very good computational resources. Otherwise, it is prohibitive. So in meta-learning, the goal of the training model is to quickly learn a new task from a small amount of new data. And the model is trained by the meta learner to be able to learn on a large number of different tasks. And the key idea underlying our method is to train the model's initial parameters such that the model has maximal performance on a new task after the parameters have been updated through one or more gradient steps computed with a small amount of data from that new task. And the meta-learning problem treats the entire task as a training example. So when we say what is an episode in few-shot learning, so it's a popular technique and it consists of organizing training set in a series of learning problems. So meta-learning is a more general way of few-shot learning. It's just one of them, but it's more general. And each episode is composed of a context dataset used for model specialization and just mimicking the small datasets used for adaptation at metas or meta test time. And a query dataset, we need a query dataset as well, used to compute and optimize training loss given the specialized model. So what is the idea? Our learning process can be viewed as maximizing the sensitivity of the loss functions of new tasks with respect to the parameters. When the sensitivity is high, small local changes to the parameters can lead to large improvements in the task loss. So the goal of few-shot meta-learning is to train a model that can quickly adapt to a new task using only a few datasets and training iterations. For example, one task says that you should go in this direction, the gradient should go in this direction. Another task in a different direction. But the overall is the loss of everything that is considered. So this is the overall loss, just the addition of all of these vectors. So we have a distribution. Now, for example, if H is 1 is just the IID in traditional machine learning, we think everything is IID, but in practice you will see that it's too far from reality. And so we have distribution over tasks. Instead of traditional machine learning thing, we have a distribution over some data, we have distribution over tasks, which is more general, more natural, more systematic. And so in the inner loop, we calculate the theta for each task. For example, for I equal to 1 or second task or third task, or depending on how many episodes we have. And finally, this gathers everything, because if we sum, it's just like multi-objective. What is multi-objective? If you watch my lectures on multi-objective optimization, you see that it's a summation. For example, the technique of scalarization in multi-objective optimization, you sum over all the objectives that you have. Of course, awaited version of that, which is called scalarization in the context of multi-objective optimization. But I don't know why in machine learning community they don't use the word multi-objective optimization, because and scalarization, like this idea that this is simple scalarization, is just one of the approaches to find to multi-objective optimization. And in multi-objective optimization, we have a Pareto optimal set. So all of these are solutions. All of them are solutions. Depending on further constraints, you can select just another subset of that, just then another subset of that. So I just look at this as a kind of multi-objective optimization, because each one has a different objective. You should go to a different direction. But this one is saying the big picture. It says I know the big picture. You should guide the gradient of your loss in this direction if you want to be a trade-off between different tasks. Because as I said, we have very different tasks. For each task, this is the inner loop, and you see the algorithm, this is the inner loop that you want to know the parameters, and you have the gradient of the loss, and finally you get the total. You sum all of these in order to guide the theta to go in a certain direction. And there are many approaches in supervised learning. We can define even cross-entropy loss, maximum or MSE, mean squared error loss. So this is just the cross-entropy, and this is just MSE loss. And it doesn't matter. It has an inner loop and the outer loop. The outer loop, after you have created these theta prime, you put it, but F is shared. This F that we always use is shared among. So because it is shared, because our model is just one model, so we have to combine different losses. So we add all of them, and this will converge to the final weights that are a trade-off between many different tasks. And it may not be the best for a specific task, but globally it's a very good solution. Another approach is another problem that you're facing. You may use reinforcement learning. Even in this case, that is just the sum of the reward for each loss. So the inner loop, you are doing it for each task separately, but this one takes everything into consideration, because it's just adding all of the losses for different tasks. So this is a trade-off between different tasks, because each one, as I said, says that you should go to a different direction, but the person that always can see the big picture says that you should go in this direction, because it's a trade-off among all of these vectors. And so it may not be good for task 1, it may not be the best for task 2, it may not be the best for task 3 or 4, but this is the global approach, the global direction. And as I said, mini ImageNet is hard. The state-of-the-art accuracy is still below 65%. And of course, for 5-shot has better accuracy than 1-shot, and we expect that for 20-shot we get about 80%. But what is important is that for 1-shot we still have very low accuracy. But a child can just look at an image once and understand it. So there is a big gap between the child and a machine.